So hello guys, I will start today's lecture. So in previous lecture, we learned that for extending the CNN architecture, which was used for the image classification task towards the detection task, we need to use this kind of architecture, the RLCNN network. Okay, so this approach was published in CVPR 2013. And the high-level idea is using this kind of uh, selective search boxes. So the boxes obtained from the selective search, um, and these boxes are kind of uh, filtered from the sliding window boxes. Okay, so when we use the sliding window approach, there are width multiplied by height, number of bounding boxes, right? That's too many, right? But but we can get this amount of filtered bounding boxes, which may have object inside using the selective search algorithm. Okay, and then we apply the CNN architecture for that cropped region. So actually this process is meaning the cropping of the images and cropping and applying some rescaling for these regions. Okay, because the CNN architecture, we should input some fixed dimensional input. Normally is 2 to 4 by 2 to 4, right? So we have to first crop the images using the bounding boxes detected from the selective search algorithm, and then we have to resize the cropped images to 2 to 4 by 2 to 4, okay? And then we will input it to the CNN architecture, and in the middle, we may can extract some this dimensional feature vector, right? So maybe the AlexNet may have this dimensional or this dimensional feature vector in the middle, and other CNN architectures are also similar. And then we transform it to transform this dimensional feature vector to the class labels. This algorithm, the RCNN, they used SVM, the shallow running algorithm, to transform the intermediate features towards the semantic labels. Okay. So that's what RCNN algorithm. But the limitation is like this. So the cropping operation, cropping and rescaling, they are not end-to-end trainable, right? They are not differentiable. So we cannot uh, detect object from the whole images. But sometimes it is easy to detect humans from the whole image. Let's say here there are humans, right? Uh, Sometimes we have to use some context information from the whole image when detecting the humans. So, but in RCNN, it's like we hide all other regions and only detect this bounding box and crop it and rescale it and make us to estimate which objects are these, right? So sometimes it is hard to figure it out using these cropped images to correctly estimate what object it is, okay? So sometimes we require context from the whole image, right? But that kind of context cannot be trained using this kind of approach, right? Because their gradient are broken here, right? We cannot use weight considering the whole images, okay? But considering only the partial part, okay? And also, we still have to apply the CNNs multiple times, like 2,000 times, right? So still slow. Relatively, it is faster than applying this number of CNNs, Okay, there are huge difference, right? Maybe hundreds times fast, but still it is slow. Okay, applying CNNs for 2,000 times, that is also challenging. So still we need to improve it. Okay, so this fast RCNN approach appears after that RCNN approach. So it is meaning that it is faster algorithm than the RCNN algorithm. Okay, and also what they are doing is they first apply the convolutional layers of the pre-trained ImageNet pre-trained network. Okay, so maybe the upper part of the layers they only applied to the whole image, right? Then their output is some 2D arrays. Their responses are 2D arrays indicating some feature for this whole image, but they are in the form of the 2D arrays, right? And also, because of the characteristics of the convolutions, uh, there are some spatial information is remained. For example, the features here are retaining information from this local region, and feature here is retaining the information for this region. Okay, there are spatial information remained, right? Because this is because of the characteristics of the convolution operation, right? In convolution operation, we apply multiplication between filter corner and the image pixels, right? And then output some feature vector, feature arrays, which encode features for that local regions, right? So because of that, some kind of spatial information is retained. Okay, so this local region in feature map tend to encode features for these image regions, right? And also these regions in feature map can encode the information of extracted from this region of the input image. Okay, there are some spatial information retained. Okay, so we can somehow apply some pooling mechanism on these specific regions of the feature map instead of extracting, instead of cropping and rescaling the image itself and extracting features using CNNs afterwards. Instead of this, we can first extract the 2D arrays from the whole image and then crop the features for some local regions, maybe. We can do that, okay? So, I mean, we can use the selective boxes obtained from selective search algorithm here rather than here, okay? Then we can only apply once for the convolutional layers, okay, of the CNN, okay? And which method, and also the important thing here is the bounding box, their size could be varied, okay? Yeah, it captures it depends on the size of boxes are depending on the object size, right? So the object size could vary, right? So the bounding box size, as a result, the bounding box size is varied like this, right? Let's say this is the 3 boxes obtained from the selective search algorithm, right? Then we have to make these vectors as the fixed dimensional vector, okay? We have to map this as the fixed dimensional vector. Then we can apply some FC layers after this to estimate some class probability and refine the boxes afterwards, right? If we can have a mechanism that can make fixed dimensional vector from these varied bounding boxes, then we can apply also the differentiable layers after this to map it to the class probability, okay? Anyway, the whole modules could be trained, right? And that mechanism, which can map these varied boxes, the varied boxes to the fixed dimensional vector is called as ROI pooling, okay? ROI is the short term for the region of interest, okay? And it's called as pooling, okay? So what they are doing is like this. So let's say some box from the selective search looks like this, and let's say this is the whole feature map, 2D feature map, right? Then we will apply some 2x2 ROI pooling like this, okay? We can somehow make this each region variable, right? So this region have different size, right? But important thing is we divide them into 2x2, right? Then we will select one maximum value for each region. For example, let's say this value is maximum among these values. And let's say this value is maximum among the values here, right? And let's say this value is maximum among these values. And let's say this value is maximum among all of values here, right? And then select them as the maximum value. Then this 2x2 dimensional array is obtained, and we can make it as the 4-dimensional vector, right? Okay. So regardless of the width and height of the bounding box, we can do the same approach. For example, let's say this is the other bounding box. Then we will divide it into 2x2 like this, and can obtain 4-dimensional vector, okay? And let's say there are another bounding box whose size is like this. Then we will divide it like this and select maximum values in each region and can make 4-dimensional vector, right? So this is ROI pooling. So, I mean, regardless, in ROI pooling, they don't care that each region is in different size, okay? But because we will apply the max pooling anyway, regardless of the size of the sub-region, we will select maximum value from that sub-region, okay? And then we can get this number of vector, right? This dimensional vector, okay, afterwards. So even though the bounding box, their shape is different, they can map it to some fixed dimensional vector, okay? And this vector is feature for those regions, okay? And then afterwards, you will apply some differentiable FC layers to map it to the class label or to refine the original box, okay? That is happening in here, okay? So here, they apply boxes from the selective search algorithm, and then using the ROI pooling, they map it to some fixed dimensional array, and then they reshape it to the 1D signal, and then apply fully connected layers, and then map it to 2 output. The first is the class probability for those regions, which objects are inside, right? And the other thing is refined box location. Okay, define box width, height, and their center x and y. Okay, this is their output. Okay, so the overall pipeline is end-to-end differentiable from the input image to the last output. Now, okay, the core idea is instead of applying boxes obtained from the selective search to the input image, they apply it in the 2D feature, intermediate 2D feature. And the intermediate features are retaining some spatial information. They can do this, right? And they, to map it to the fixed dimensional vector, they apply ROI pooling, okay? So this is the fast Shannon algorithm. And this is the loss function used to train this overall network, okay? So let's say the U is class, ground truth class, and 0 is indicating the background. And if U is larger than 1 equal to 1, that is indicating its object class. Okay, background is 0, and when the label is larger than or equal to 1, then it is indicating the object. Okay, and this is the predicted probability for object. Okay, and this is the classification loss, and this is the bounding box information estimated from the last output. So here, this is the this T, right? And so this class probability had to figure that these local regions are background or other object, right? And if it is object, then they apply this loss. They refine the original T, the box location, okay? So, and also this is some error loss, smoothed error loss. So, I mean, this is basically same as error or L2 loss, okay? To close the ground truth box information at to the I mean close the predicted box information to the ground truth box information. That is the error we are doing. We are applying error or L2 loss for doing that, right? But here they use smoothed error loss. So when you draw this as the graph, it looks like this. So when their values are there when the difference between these two, the ground truth and predicted is rather small, they apply this kind of curved loss function. And after that, they apply this kind of error loss. This is the L2 loss, right, squared. And outside of that region, they apply error loss. So they empirically found that this loss function converges better than the pure error or pure L2 loss. So they use this type of loss. But this is some detail, but you can think just they use some error or L2 loss that close predicted value to the ground truth. Okay. And the next thing is the faster RCNN. Even they say they made faster pipeline compared to the fast RCNN, right? So this paper is also published in the same year as in the NIPS paper. And they say this part are same as the fast RCNN algorithm. They use this type of intermediate response map, 2D response map. But what they do here is they, instead of using selective search algorithm to secure the object bounding box, they infer it. Actually, they infer this as well using this region proposal network, which is the CNN algorithm, okay? So the selective search algorithm, it involves the clustering of pixels. And this is some iterative algorithm, takes time. And also the result is not optimal, right? But here they want to make the boxes using one pass inference using the CNN. And also they want to learn these boxes from the data, okay? So this fast CNN, they are a little bit faster than the fast CNN, and also it is more accurate, okay? So it solves the bottleneck in the region proposal of fast CNN, okay? They infer it additionally, okay? So this is the comparison between RCNN, fast RCNN, and faster RCNN. So here they first extract 1,000 to 2,000 regions, right, using selective search algorithm, and apply CNN per each region and classify those features, okay? So still slow and not optimal because they cannot learn from the whole image, but from the cropped image, right? But in fast CNN, they apply CNN on the entire image and first extract the feature map regions and then make the feature map using ROI pooling and then map it to the class label afterwards, okay? And here they further solve the heuristics remained in object proposal algorithms, okay? So this is the comparison between these three algorithms, RCNN, fast RCNN, faster RCNN. The time becomes faster, right? It takes less time for one inference, right? And the accuracy, actually, this is two are indicating accuracy for this data set, okay? So you can see the accuracy becomes better and better, right? Okay. So by the schemes, these RCNN, fast RCNN, fast RCNN, they are becoming better in performance, and also it becomes faster, right? So this is the CNN-based object detection pipeline. Okay, fast RCNN is quite popular until these days. And this is the and then we want to explain the transformer-based algorithm. But before that, I have to explain about the RNN method and also the LSTM method, and then I will explain about the transformer, and also will explain the DTR algorithm, which was extended towards the object detection task. Okay. Okay. So this type of RNN algorithm was used to tackle some sequential data. Means there are some same format of data in T frames. Okay. This type of data is called as sequential data, right? Same format of data are in given considering their orders, and their length is, let's say their length is T, then this type of data is called as sequential data, okay? So to process this type of data, we normally do this kind of thing. So let's say X1, X2, and XT, these are sequential data given, okay? Their length is T here, right? And then if they input X1 to this network, then this feature is H1, okay? And they apply another network, and output the O1, right? And when we apply X2 as the input to this network, we can independently do that, not considering previous frames result, right? But it is known that when we consider their previous, when we get some information from the previous frame's feature, this output becomes dependent on this O1, right? So for this sequential data, it is known that considering their sequential, their, how to say, their previous frames information is helpful to obtain the more robust result, okay? We can, of course, do this type of class, do this kind of job independently, not considering the previous frames information, right? But compared to that, considering their relations is better in general, right? So for doing that, this type of recurrent neural network is frequently used, okay? So we can, how to say, expand the whole operation like this, but sometimes we can compress that kind of operation like this. So here for xt, we can obtain the ht, the feature for xt, and can map it to ot, the t-frames output. And at the same time, we recurrently use the previous frames feature to it again, right? We can compress the things like this, okay? But one thing is, in this recurrent neural network, the vanishing gradient effect can be happen, okay? So when I explained the ResNet, I already explained this vanishing gradient. So actually the gradient calculation, maybe here the loss will be located. And let's say we have to calculate some parameters in here, right? Then when calculating DLD sector, we have to multiply all the gradient in between these things, right? And normally the gradients are less than 1. And if we multiply the values, which is less than 1, multiple times, for example, 20 times, then the value becomes 0 because of the precision, okay? So the computer have some fixed dimensional bit. They assign fixed dimensional bit to represent some floating value, right? And if the floating value is becoming small and small, the PC cannot sometimes represent it properly if they are too small, right? And simply they represent it as the 0, right? So because of that, if the values are too small, it simply becomes 0, right? And it happens when we multiply multiply gradients for deep networks, okay? If the connections are too deep, the gradient becomes too small and it eventually becomes 0, okay? Actually, because of that, this RNN sometimes not that good. So, and also this is non-trivial to parallelize. So for each sequential data, we have to conduct this, uh, this maybe separately. And also because this T could be buried, so it is hard to parallelize. That's the problem in this dealing with this sequential data. Anyway, for solving the gradient vanishing gradient effect, this LSTM was proposed. Okay, so they somehow have some control unit for controlling how much they forget and how much they reuse the current frames information. So by doing that adaptively, this LSTM performs better than the RNN. Okay. So basically what they do is, this is the input signal, right? And they have this C and H, okay? I forget the name of this. Okay, cell state. This is some cell state indicating some cell state, and this is some feature, okay? And this was obtained from T-1 frame, and this is also obtained from the previous frame, right? And this is the input to current frame, right? And we will first estimate the forget bit using by concatenate. This is concatenating the current frame's signal input and the previous frame's the hidden state. And this is the weight we will learn. And also this is the bias we will learn. This is same as the linear operator, right? By concatenating this T input, T frames input, and T-1's hidden state, we make some forget bit, okay? This is sigmoid, so this value is in between 0 and 1, right? And also this information bit, that is also same as before, but using different W weight vector and different bias. We have to actually learn this too, okay? And again, this C hat is also obtained like this, okay? So this is the T frames cell state, okay? This is also obtained from these two information. And then they do this. So from the previous cell state, they select which bit, which dimension. This is some vector. So which dimension they will forget. Okay, they estimate that. And also here they estimate which dimension they will use from current frames cell state. I mean, this tilde is indicating that this is some temporary value, and this is indeed becomes the T frames cell state. T frames cell state. This is T-1 frames cell state, and this is the some temporary T frames cell state. And this will choose which dimension they will use, they will retain, and this indicates which dimension they will forget from the T-minus frames cell state. Okay, so using these two, FT and IT, they can select which information they use from temporary T frames cell state, and F, by using F, they decide which information they will lose, they will delete from the T-1 frames cell state, okay? And they combine this to make the real T frames cell state, okay? So in here, they adjustly decide which information they lose, and they not lose, some they delete, and which information they retain. They can adaptively decide that. And also the output is obtained from the this input using some other parameters, okay? And this becomes the information. So CT, that is cell state in T's frame, right? It is decided from here, right? And then it again decide how much they will output it, okay, by this output vector. And this HT is uh, outputted for next frame, okay? So this is recurrently do for next frame, okay? So this LSTM looks similar to, basically they are similar to this RNN, but have some modules to adaptively decide which information they forget and which information they will retain. Okay. So because of that, this LSTM performs better than RNN by reducing the vanishing gradient effect. Okay. Is forget input and output gate. They control the information to lose or to gain. Okay, and so they can provide some ability to prevent the vanishing gradient. Okay. So this was the actually this sequential data is normally seen in the NLP tasks, natural language processing task. So for example, maybe we can translate I'm a student to some French language like this. And when doing that, this type of LSTMs are used, okay? So the input, the English's feature have to be obtained by seeing all the English sentence, right? And for doing that, we apply LSTM sequentially, same LSTM but sequentially, and the final frame's output becomes the feature vector for this English sentence, okay? And then what we do is inputting this feature at the same time, input some start. This is the start token indicating we will start the translation. Then if we input it here LSTM with some feature vector, then the first word is outputted, okay? And then we will input to the LSTM the first French word we got from the LSTM output. And at the same time, we translate the feature to the next LSTM. And then we will get this next word. And then we will again input it to LSTM and translate some feature to the next frame, okay? And it happens when we got this EOS. That means it ends, the translation ends, okay? So when we got this EOS, we iteratively apply this LSTM, okay? So anyways, by doing this kind of sequential operation, many NLP tasks, okay, is done, okay? Because their data are mostly sequential data. So in NLP, they frequently use this LSTM, okay? But here, transformer appears, okay? So as you see here, it is hard to parallelize the LSTM operation, okay? It means we always have to one by one input the sequence, right? We have to get this feature in the middle sequentially, right? We cannot change order of these two operations, right? Also for decoder is same, right? But in transformer, some researchers propose this transformer to make this process parallel, right? Okay. But before that, I have to make this clear. So encoder, what encoder is doing is encode the features of the input sequence, right? And decoder, they are generating some output sequence from the feature and the the autoregressive output. Okay, so this we are inputting the previous output, right, to the decoder, right, as well as the feature, right. So that's what decoder is doing. Okay. In transformer, encoder decoders are similar, but they are performing this parallelly. Okay. So they input this I am a student at the same time, simultaneously, okay, to the encoder. Then this encoder generates some feature of this I am a student, okay. But decoder performs sequentially as well. So by inputting this feature here, decoder, and they have to input some start token, and then this first word will be here, and then it input these two token, and then this will appear in the output of the decoder. And also you have to also input these three input, then this will appear in the output, and so on. Okay, you did this until EOS is obtained. Okay, so the encoder part is parallelly performed, but the decoder part is still sequentially operated in the NLP tasks. Okay, this is the transformer, and because this operation is parallelly done, so you have to somehow indicate this I am a student is having some sequential information. So for example, we are knowing that I is in the left position to the M student, right? Okay, but this transformer encoder cannot know that. Okay, so to encode it, we first have to map it to the some feature vector and have to add this type of positional encoding vector. So this is some vector indicating the positions of words. Okay, we have to add this vector to the embedded feature vector for each input. Okay, so this added feature becomes another new input to the transformer encoder. Okay, and decoder we also do that. Okay, so we had to add this type of encoding, positional encoding. And there are actually three mechanisms in transformer. Actually, the self-attention mechanism and masked self-attention mechanism and the cross-attention mechanism. So encoder-decoder attention, and many times it is called as cross-attention. Okay. So I will explain this part. And in many literatures, they are representing transformers like this. And sometimes this type of figures are shown, but basically they are same. So this is indicating input here, right? Input here. And this is actually encoder. This part is encoder. And this is the decoder. And this is the input to the decoder. So this part is denoted here, right? And this is decoder, and this is the output obtained here, right? So basically, this figure and these figures are same. And okay, this is the paper where the transformer was first proposed. I will first explain about the self-attention mechanism. Actually, this is the most primitive operation used in the transformer. Okay. We have to add positional encoding first to the input vector, right? And what they do is they make three vector query. This is called as query key value. And we obtain it from the original input vector. We have to apply some weight, and by multiplying weight to the original input, we get query key vector. So WK, WQ, WV, those are parameters we have to learn. Okay. Okay. And what they do is we have I am a student. Okay. And for encoding this word I, we use four key values. Okay. For one query, we use four key values because there are four words here: key I, key M, key O, key student. Okay. Okay. And we multiply those two, and this becomes some attention between these two words. So I and I, we can get some attention between these two, and IMM, we can obtain some attention between two using by multiplying this query and key. And this is kind of measuring some similarity, some relationship between these two words. Okay. Okay. And then we can multiply this value. This is attention value we obtain from this query key multiplication. And then we multiply this value with the value, okay, value. This becomes the feature, new feature, okay. This by multiplying query and key, some relationship between these two words are obtained. This is some scalar, and then we will eventually multiply value vector to those values, okay. Then we can get some feature, okay. This is the self-attention mechanism, okay. But this same operation can be parallelly done by applying this kind of query matrix with the key matrix, okay. By multiplying these two arrays, we can directly get the attention matrix, and then we can multiply value, and then we can get forward value matrix at once, okay. This is the self-attention mechanism, okay. So it is kind of capturing the dense relationship between each input, okay. This is let's say there are three input, then this self-attention mechanism is capturing their dense relationship and make some feature considering those dense relationship between words, okay. And we do this for using, can be obtained from one head actually, but we can apply this, how many, we did multiple times anyway. That is actually called as multi-head attention, okay? This is one attention, but if we have this operation multiple times, then they are called as multi-head attention, okay? And we concatenate this output, okay, and multiply WO afterwards, okay? And this becomes the final feature, okay? We can obtain this attention result multiple times by concatenating their output and multiplying this weight for that, okay? Okay. This head I is indicating one attention result, right? And we can concatenate it and multiply WO to get the final output, okay? And that becomes our kind of final feature, and we can map it to the other output afterwards, okay? Okay, so this is indicating this operation again, okay? And this is the masked attention. So actually, the self-attention happens here. So from the input, we make query key value, okay? And then this multi-head attention is applied to get a result, okay? Anyway, this is indicating the self-attention using multi-head attention, right? And this becomes the encoder. This constitutes the encoder. But there are slightly different operation, which is called as masked attention. That happens in the first part of the decoder, okay? This is happened because, as I mentioned before, the decoder is happened in the sequential manner, right? So first, this token only is inputted using some feature vector from the encoder. And we have to output the first word. And then next, we have these two token input, okay? And then output this. And next time we have this and have to output this. This is happened in the sequential manner, right? So to model this, somehow we mask some of attentions obtained because when this SOS is obtained, we have to consider it only, okay? And for obtaining this JE, we will have attention for the first SOS and JE, right? We don't see, we can't see the later words, right? When finding the attention value for former word, right? So SUIS, it can see itself and previous words, right? And this see itself and previous words, okay? So on purpose, we mask the later word when calculating the attention for previous word, okay? So actually, this is the masked attention, okay? It happens inside the decoder because of the decoder operation, okay? And here, we have to somehow mix the information from the encoder to the decoder. Actually, this happens here. So the query is come from the previous layer's output in decoder, right? But key and value, those are come from the encoder feature, okay? Encoder's final output, okay? And they are actually mixed. So in here are French outputted from the intermediate output from the decoder. And this is the feature obtained from the encoder, right? So we somehow apply the attention for heterogeneous signals, okay? That happens here. And because of that, it is called as cross-attention mechanism. So their input is slightly different here, right? And then, using some MLP, and we can make some feature and apply some linear layer and map it to some probability, right? Okay, this is the transformer architecture. Okay. Okay. Actually, transformer, though it is composed of attention mechanism, three types of attention mechanism. Here, the self-attention is used. Here, the masked attention is used. Here, the cross attention is used. Okay. Okay. Anyway, so you have to feel that this attention mechanism is composed of plus minus multiplication and division, right? So they are differentiable, right? So whole pipeline could be learned, right? All of the weight in the middle here, WO and W, K, Q, V, those can be trained, okay? So anyway, using the same PyTorch training code, you can train this transformer, right? Okay. But I mean, this transformer is gradually replacing the CNN algorithm in vision domain as well. And this DTR is the first maybe architecture proposed for the object detection task. Okay. Uh, I mean, CNN is capturing some local information, right? So filters are applied rather locally to the image regions, okay? But this transformer is kind of mechanism considering all the dense relations between input, okay? So in that sense, transformer has some possibility of suppressing the CNN operation, right? When representing the features. So people use this, and indeed, it is replacing CNN in many applications. Okay, and this is the first object detection pipeline made by the transformer. Okay, so and I will explain this. Uh, yeah, this is the first transformer-based architecture for object detection task, and better it performs better than fast RCNN without any post-processing. Okay, so basically it has similar architecture to the transformer we have seen, right? But because it is using the image domain signal, previously it is the language data, right? It uses the sequential data, right? But basically this DETR is proposed to use the non-sequential data. That is huge difference, okay? So the input here is image, which is non-sequential data, okay? So, and we use pre-trained CNN network, ImageNet pre-trained CNN network here to make it to 1D vector first, okay? And then we apply 2D positional encoding like this here, right? And this becomes the image feature itself becomes the input to the transformer encoder, and some feature vectors are encoded using the self-attention mechanism. Okay, and there are some vectors called as object queries. Okay, I will explain this later. Anyway, uh, here the transformer decoder is performed using the cross-attention mechanism to output some feature vector for each object queries. And then if each object queries are mapped to uh, this class and bounding box set, okay? Actually, there are normally 200 to 300 object queries. They are inputted as the input to the decoder, okay? But here you have to care that you have to notice that the object queries here is not having any sequential meaning. Okay, previously in here, this decoder input have some meaning, right? Having some meaning as well as it have some order, right? But here in DTR, there is no sequential meaning for these object queries. And also, this value is not having much meaning, okay? but they are actually some vector, and they are actually trained during the training stage. Okay, vector which have some arbitrary floating values, they are trained during training, but there's not much meaning. Okay, we just input some floating values here, which was trained during the training. So this is called as learnable parameters. They are just called as learnable parameters. Okay. And anyway, input image is inputted, and image features are obtained in this as these dimensional arrays. Okay, and these are rather rescaled. Okay, and actually these tokens, these inputs are having this dimensional uh, vector. Okay, actually there we transform this dimensional vector to d-dimensional vector using some linear operation, and we reshape it to the 1D signal. And so yeah, each input having this dimensional signal, right? Okay. And these object queries are also having same dimensional signal, but they are having this number of, we are having this number of object queries. Okay. 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 This for each input, it has d-dimensional vector, and this is the number of vectors, number of input. Okay. And from this output, which also have d-dimension, and we apply linear operation here, some MLPs, and map it to the class and box locations, similarly to versatile CNN. Okay, this is actually the DTR. Okay, so you can in detail see the architectures of the DTR like this. So this is the encoder, this is decoder. And image features are input to the encoder, and they are mapped to key query values using some, they are first added with some positional encoding and transformed to key query value. And self-attention mechanism is applied to get the feature vector, okay? And the object queries are some learnable parameters, some floating values, which is learned during the training. So, I mean, some loss functions are obtained here, and some parameters are learned during the training, right? And also these floating values are also updated during the training, and they are fixed and used for the inference. Okay, they are not having any meanings, but they are the vectors which make this DTR work. Okay. Okay, and these object queries are also used as the query key value, and they are using the self-attention is also used here because there's no sequential meaning between object queries. Previously, because the input to this decoder is having some sequential meaning, so we do mask attention here, but here self-attention is still used. And here, the object queries are cross-attended to the encoder's feature, and they are mapped to some feature vector here, and they are mapped to class and bounding box information at the end of the transformer, at the end of the DTR, okay? And this is another plot, okay, showing the decoder structure in more detail, okay? And the other important thing you have to be aware of is this, okay? So basically, in the output of this output is having n set, okay, n set of decoder output. They are mapped to n set of class and box, okay. We can obtain the n sets of, and normally n is 200 to 300. So from the one image, we may get some many sets of class and bounding box information. Okay, they are we can get 200 to 300 box and class information, right? And during training, we have to somehow match it. This is our ground truth space, and this is our prediction space. We have like 200 to 300 output predicted from the transformer, right? But in ground truth, we have like 2 or 5 objects, or sometimes we may have more, right? But anyway, our ground truth would be like this, okay? Mostly it has background as the class, and bounding boxes are none, okay? Because it I mean only two, let's say only two box and class are there in ground truth, then we can make two sets here indicating their bounding box location and size and indicating the class within it. And for remaining number of set, we assign some zero class indicating background and known for bounding box information, okay? And for the prediction, we may obtain some background prediction, but we can have some random number of predictions, right? And among them, we have to first match have to match the prediction with the ground truth. And we will match the most plausible output prediction to the ground truth, okay? So if prediction is similar to our ground truth, they are matched, okay? We have to have the match process first, okay? And unmatched prediction is matched with some some ground truth which has known and which has the background as the class and known for bounding box, right? So we can actually remove these predictions, okay? Okay. So the training part is happen in two stages. First, we have to match the prediction of our transformer and ground truth, okay? And then we apply the cross entropy laws or the L2 MSE laws for matched samples, okay? So that is actually happening here. So this is the matching part, okay? And this is the actually training part. So this is the cross entropy laws, and this is the MSE laws, okay? This is backpropagated actually, but before that, we have to find this best match between predicted values and ground truth value, okay? This is all possible configurations indicated here, right? This is ground truth having just two as the true object, and all others are having background as class and known for box. But prediction can have multiple predicted values, right? But and this is indicating all possible configurations here, right? Among all possible configurations, we have to find the sigma head, which have configurations like this, okay? Then we will make this close to this ground truth, and we will make this close to this, make this close to this, and so on. if the found sigma is like this, then still we can make this close to this and close to this, and this close to some null values, right? Anyway, we have to find one best match, and that's actually called as bipartite matching. And then we minimize loss for found set. Okay, that's actually happened during the training of the transformer. Okay, so and by doing this training, we will learn the parameters, the key transformation metrics, and this WO and WKWV. Okay. And this is the result obtained from the DTR, and it is comparing with fast RCNN. And we can see their DTR's performance is better than the fast RCNN. And also, but this is sensational because in fast RCNN, there are some post-processing, which is heuristic, but DTR, they compare this to the fast RCNN without that kind of post-processing. So without that kind of heuristics, fast DTR outperforms the fast RCNN. Okay. So this is the end of today's lecture. Thanks a lot.